In the last video, we found out how many grams of carbon dioxide we ended up with if we burned 0.321 grams of ethene in an excess of oxygen. We went through and we found out that it was this much. So, now that I have that, I'm going to write that under here. So, 1.01 grams of CO2 were produced. Well, now let's say I wanted to find out how many grams of H2O we had. Well, we're going to do the same thing. We're going to set this up with dimensional analysis. Only we're going to start with grams of what we had, and we're going to end this time with grams of H2O. So grams of H2O goes on the right side. Now, since we've already done this, I don't want to erase all of this stuff because it's good, right? Like, we're still going to need this right here. So once we get into CO2, we can pretty much forget about that. But this time, we've already set this up, right? So we went from grams of ethene to moles of ethene. Now that we have moles of ethene, we could get moles of water. I'm going to put moles of ethene on the bottom, moles C2H4. And I want to go into moles of water, H2O. Okay? So again, to find that ratio, we look at the coefficients here, and we see that for every one molecule of that, or mole of that, we get out 2 moles of H2O. Now, can I go from moles of H2O to grams of H2O? Yeah. We're going to put moles on the bottom. That's moles of water to grams of water. And we're going to need to find out what that is. So I'm going to pick up my calculator. And let's see. So 2 H's, so 2 times the weight of hydrogen, which is 1.008, 2 times that, plus 1 times 16.00. Enter, and we get 18.016 grams of H2O in every 1 mole. Now let's check. Does everything cancel out? We had grams of ethene, moles of ethene, moles of H2O, grams of H2O, which is what I wanted to find out. So I'm going to go through and plug this in. 0.321 grams times 1 divide by 28.052 times 2 divide by 1 times 18.016 divide by 1, and we get 0.413345 grams of H2O. Now let's think about significant figures. Again, we have a lot here and here. We're going to be limited by this. We're not limited by this because this is a conversion ratio. It's an exact measurement. It's like saying 5 fingers on one hand. We don't need to worry about that. So this one we don't worry about. The one with the least amount is this one, which is 3. So this is going to be limited to 3. So our final answer for grams of H2O is 0.413 grams. Now, the only thing we don't know so far is how much oxygen did we use? Well, there are a few ways to figure this one out. And the way I'm going to do first is with moles, because moles is pretty straightforward, I think. So let's see. How could we go from grams of this? We always start with what we know, right? This was all calculated, so I'm going to not really put much faith into that. I'm going to start off with what I know, which is 0.321 grams of ethene, C2H4. And I wanted to find out, let's say, how many grams of O2 did I use? actually, let's say how many atoms of O2 were used up. Let's do that. So I want to go to atoms of O2. So we're going to have to do dimensional analysis. So, of course, with stoichiometry, we go from grams to moles without even thinking about it. Grams to moles. We have grams to moles. This is grams of ethene, C2H4, to moles of ethene, C2H4. And I erased it. I shouldn't have, but I'm going to do it real quick. 2 times 12.01 plus 4 times 1.008, and I get 28.052 grams for every 1 mole. And now I could use these ratios again. Now that I'm in moles, right, I could go from moles of ethene, which is here, moles of ethene, C2H4, into moles of oxygen, moles of O2. So we know there's 1 mole of ethene for every 3 moles of O2, because that's what this tells us right here. And now, how do I go from moles of O2 into atoms of O2? Or, ooh, I shouldn't have put O2. Atoms of oxygen. There we go. So now we're in moles of O2, which is a molecule. And we want to go into atoms of oxygen. So we need to be really careful about this. So, okay, I'm just, without even thinking about it, let's say I don't know where to begin with this. Without even thinking about it, I'm going to put moles on the bottom because I know I want to get rid of it. So moles of O2. So ultimately I want to get to atoms of oxygen, of just oxygen. So I want to go to, let's see, I'm going to go into molecules first. So I know that in 1 mole of O2, we have Avogadro's number, 6.022 times 10 to the 23rd molecules. Right? Because if this is O2, and you have 3 moles of that, then it's 3 times Avogadro's number of these. So now that we're in molecules, now we could say that in every molecule, there are how many atoms? Well, it's O2, right? So in every 1 molecule, there are 2 atoms of oxygen, right? 1 molecule of O2, 2 atoms of oxygen. That seems pretty reasonable. So let's go. 0.321 times 1 divided by 28.052 times 3 divided by 1 times Avogadro's number, 6.022, hit the E key, 23rd, times 2 divided by 1, and I get 4.134597 times 10 to the 22nd atoms of oxygen. Now, just out of curiosity, how much does that many atoms of oxygen weigh? Well, let's see. I'm just going to put 4.13 atoms, times all that, atoms of oxygen, times, I need Avogadro's number, right? So 6.022, 10 to the 23rd atoms in 1 mole. Now I could go grams to moles, right? Or moles on the bottom. Moles of O, just oxygen, sorry, not O2. Moles, 1 mole of oxygen is 16.00 grams. So let's see. Take that, divide by 6.022 e to the 23rd times 16. We get 1.098.